So we're going to cover just the very basics of probability. The rest of statistics is highly, highly interwoven with probability because that's what we use to make predictions and inferences based on the data that statistics gives us. So this is just going to be a very cursory level as far as probability concerned. We don't have time to go much deeper, but there is a lot that goes into this course. So some definitions to kind of go through real quick. A probability experiment, that's an action or a trial in which specific results are obtained. So a count, a measurement, survey results, responses, things like that. So when we do an action, that is considered an experiment. The outcome is the result of one trial in a probability experiment. So we can survey a bunch of people, and the response that we get from every single person is an outcome. We can flip a coin. Every time we flip the coin, the result that we get is an outcome. Sample space is the set of all possible outcomes. So for example, when I flip a coin, I can get heads or I get tails. That is my sample space. If I roll a 6-sided die, I can get a 1, a 2, a 3, a 4, a 5, or a 6. That is my sample space, the possible outcomes. The event consists of one or more outcomes and is a subset of the sample space. So the event could be, I get a heads. Okay, that's part of my sample space. The event could be students that have a 3.0 GPA or above, and the students that fall in that category, that would be that event, okay, out of all the students in their relative GPAs. So one thing that we can do to help us kind of identify the sample spaces and the events is commonly used is a tree diagram, where it takes the different possible outcomes for the various trials and then creates a list of all the different combinations that we could arise. So when we're surveying about blood types, most commonly we look at the blood type among A, O, B, and AB. And then we also include whether they are Rh positive and Rh negative. So a lot of times you'll see people say, oh, well, my blood type is O positive or B negative. So we can use a tree diagram to kind of break all of this down and identify the sample space. So if you're blood type O, you could be either O positive or O negative. And if you're blood type A, it's the same thing. It could be A positive or A negative. And we follow that same pattern for B and for blood type AB. And so when we look and we see my sample space contains 8 different possible outcomes. O positive, O negative, A positive, A negative, B positive, B negative, AB positive, and AB negative. 8 different outcomes. A simple event is one that consists of a single outcome. All right? There's only one way that I can achieve that. So a simple event would be if event A was being blood type A negative. Okay? There's only one way I can arrive to that combination. But if my event was being blood type A, well, there's 2 possible outcomes. I could be blood type A positive or I could be blood type A negative. That would be a not simple event. Another example is if I'm flipping a coin and I'm rolling a die, if I'm specifically saying, all right, event A is if I get a heads on the coin flip and I roll a 3 on the dice. There's only one way for that to happen. I have to get a heads and I have to roll a 3. But if I'm looking at how tossing the coin and rolling an even number, because now I have more ways of getting an even number, it's a not simple event because I have 3 different ways that I could reach that specific outcome. I could flip and get heads and a 2, I could flip and get heads and a 4, or I could flip and get heads and then roll a 6. So I have 3 different ways that I can get that outcome. Then it is a not simple event. So you want to think very carefully about, can I get that outcome just one way, or can I get that outcome more than one way? And that will determine simple versus not. So for quality assurance, you randomly select a machine part from a batch that's been manufactured. The event A, is going to be selecting a specific defective machine part. Is that going to be simple or not simple? What do we think? is selecting a random machine part. Simple or not simple? Simple. You can only grab one. That's it. That's the part. It's either effective or it's not. It's a simple event. You roll a 6-sided die. Event B is rolling at least a 4. Simple or not simple? Why? Like what? What outcomes could we get that is at least a 4? At 4, 5, and 6. So if I'm looking at, I can roll a 4, at least a 4. If I roll a 4, then I match the outcome. If I roll a 5, I match the outcome. If I roll a 6, I match the outcome. So it's not a simple event because there's more than one way for me to have that outcome. Now, our fundamental counting principle is a way to kind of speed up the process of identifying the size of our sample space. How many different possible combinations we have. It says that if an event can occur in some number of ways, we call M, and then another event can occur some number of ways, we call N, and we can continue that, an event for any given number of ways. The total combination of all the different events will be the product of those numbers. So for each event, how many times it shows up, how many different ways we can achieve that event, multiply, 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 over and over and over and over and over. So we're looking at car manufacturers. When you're purchasing a new car, you have options for the manufacturer, you have options for the color, you have options for the size of the car, and there's lots more options, but to keep it simple, we're going to look at these 3. And we want to identify the number of different ways that we could select a car. How many different options of car do I have to choose from? Well, our fundamental counting principle says, okay, well, you take the number of options for your first event, you take the number of options for your second event, and you take the number of options for your third event, and you multiply them all together. Well, how many different options do I have for manufacturer? 3. How many for car size? How many for color? So we do 3 times 2 times 4. And we get 24 different possible combinations among those choices. Now, obviously, cars have a lot more choices than just that, but that gives a simplified example. If we want to use a tree diagram to kind of verify that, what we can do, you don't have to write this down, but just kind of know where it's coming from. If we're starting with, say, the manufacturer, and we have 3 different manufacturers we can choose from. We can choose Ford, we can choose GM, and we can choose Honda. And then for each of those categories, we can choose either compact or midsize. And I can do that for all of those, compact, midsize, compact, midsize. And then once I choose compact or midsize, then I can break it down even further as being either white, green, black, or red. And I can do that for all of these, white, green, black, and red, white. I'm running out of room here. There we go. White, green, black, and red. White, green, black, and red. I could do that for every single one and then count up how many ending nodes I have, and it's going to give me 24 because I've got 4 here and 4 more 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 here to give me 24 different combinations. So our fundamental counting principle speeds up that process for us to look at the total number of combinations. Let's take a look at a security system. 4 digits. Each digit can be any number between 0 and 9. So how many different numbers is that to choose from? If I can choose any digit from 0 to 9, how many options is that? 10. Okay? 10 different digits to choose from. So we want to look at how many different access codes are possible given these different criteria. So our first combination is that if each digit can only be used once and not repeated. And so we look at each different spot in our access code. And so for the first digit, how many different numbers can I choose from? 10. I could use any of my digits, 0 through 9. So I have 10 different options I could choose. Now for the second digit, I can't use whatever was used in the first one. So how many options do I have to choose from now? 9. And then for the third digit, I can't use either of those two. So how many do I have to choose from? 8. And then for the fourth one, how many do we have? 7. So we take 10 times 9 times 8 times 7 to get, I think it's 5,040, if I remember correctly. 5,040 different possible combinations if we're following those specific criteria. Now, instead of saying, okay, well, numbers can't be repeated, we say, well, what if they can? Okay, we still start with 10 for the first, and since I'm allowed to reuse digits, how many options do I have for the second? And the third? And the fourth? So they all have 10 options. So we have 10 times 10 times 10 times 10, which is 10 to the fourth, and we have 10,000 different options. So just by removing that limiter of saying, well, we can't repeat numbers, we've doubled the number of possible combinations that can be used for that security code. For our last one, each digit can be repeated, but our first one cannot be a 0 or a 1. So how many options do we have for the first digit? 8. How many do we have for the second? 10. And the third? 10. And the fourth? 10. The only limiter is on that first one. It can't be 0 or 1, so it has to be 2 through 9. But outside of that, we can use 0 through 9 for the rest of them. So 8 times 10 to the third, and we get 8,000 combinations that we can use for that security code. So our fundamental counting principle helps us in determining the size of our sample space. And the size of our sample space is useful when we're looking at different types of probability, especially when we're looking at some compound events. So we have three main types of probability: classical, empirical, and I'm forgetting the last word, subjective. So classical is the most basic level of probability, the first thing that we look at whenever we're looking at probability for the first time in our lives, where each outcome in a sample space is equally likely. Okay? There's nothing that's going to change your chances of getting a specific outcome. Flipping a coin, rolling a dice, spinning a spinner on the roulette wheel. Okay? All of these have an equally likely chance of happening. So our classical theoretical probability is just going to be the number of outcomes in our event. Okay? So how many different ways can we get that specific outcome, divided by the size of the sample space. And so we look at a six-sided die. Well, what is the size of the sample space when I roll a six-sided die? How many outcomes are possible? 6 outcomes. Right? So my sample space is 6. So anytime that we are trying to find the probability of an event, we're going to be dividing by our sample space of 6. So we look at event A, rolling a 3. Okay? How many different ways can I roll a 3 on a six-sided die? Just one. There's one side that has a 3 on it. So I can roll 1 out of 6. When we have fractions, we want to simplify them. We can also write our probability as decimals and percents. It just kind of depends on what we need. If we have fractions like 1/6 that are repeating decimals, we will have to round them at some point. So I'm just going to round them to the nearest percent. If we take 1 and divide it by 6, we get approximately 0.17, which is also approximately 17%. So there's 3 ways that you will see probability being written. Most often, especially when we're doing calculations and such, we leave it as a fraction or a decimal. Now let's look at event B, rolling a 7. How many different ways can I roll a 7 on a six-sided die? 0. Can't happen. So we have a 0% chance of rolling a 7. How many different ways can I roll a number less than 5? 4 ways. So we get 2/3 as our probability. I can roll a 1, a 2, a 3, or a 4. All those are all the different events that are less than 5. And normally we'll see this probability written, I should have done that. Let me move this over. A lot of times you'll see, okay, the probability, my event is a 3. Probability of rolling a 3. Probability of rolling a 7. Probability of getting less than 5. Okay? You'll see that notation where it's P and then E is the event, whatever it is that we're looking for. Statistical probability is based on observations from experiments. So instead of saying I have a 1/6 chance of rolling a 3, I take that die and I roll it 20 times and I count up the number of times I actually get a 3. Is it always going to be exactly 1/6? No, but it's going to be close to it, hopefully. And so we're measuring the frequency that an event actually happened and dividing it by the number of times we did a trial. So if I rolled the dice 20 times, I did 20 trials. And then the number of times I actually got a 3, that's the frequency of the event. We use this a lot when we're taking surveys. We have a survey of randomly selected adults about how much they read or how they read their books in a year. We surveyed 1,502 adults, and we've got the information in the pie chart. What's the probability that the next adult surveyed read only print books during the year? So we're trying to find the probability of the event where they read only print books. So the probability that they read only print books. Well, based on our results, what is the frequency that responded with only print books? 560. Our frequency is 560. What is our total frequency? 1,502, because that's how many trials were done. That's how many surveys were done. And then we got 560 results that matched up with that event. And so we can simplify the fraction. We can write it as a percent. So we get 51 over 501 over. No, I'm looking at the wrong thing. 280. 280 over 751. Okay, which is approximately 37%. Okay, so about 37% of the time, and that's we have a 37% chance that the next person that we ask is going to say only books, only print books. We have another survey about social media use. 3,000 were surveyed. Probability that the next user surveyed is between 25 to 34 years old. What's the frequency of our event? 765. The frequency of that event is 765. What is our total frequency? 3,000. Okay? And so we can simplify our fraction, 51 over 200, which is approximately 26%. Approximately 26%. Our last is subjective probability. It's based off of intuition, an educated guess. Okay? We have previous data that suggests a certain trend. This doctor performs this surgery, and a lot of the time, his patients have a full recovery, and it's successful. Okay? It's based off of previous knowledge, but generally we use this when the situation is so complex, there's so many different factors that we can't keep track of everything, and we don't have precise data to get an empirical result. We're just comparing it to something similar, and so we're making an estimate on the probability, okay, based on prior experience. So we can classify each type of probability. Let's look at these different events and determine whether it's classical, empirical, or subjective, and be able to explain why. And we're looking at those three definitions. Is it something where the sample space, every single event has the same probability? Is it something based off of repeated trials? Or is it something that's based off of prior knowledge and is an educated guess? And that's going to determine whether or not it is which of those three. So the probability that you get an A on your next test is 90%. Do we think that's classical, empirical, or subjective? Why? Yeah. You don't know for sure. Now, if you're an A student, it's a high probability you're going to get an A, okay, based on prior experience. But you've never taken that test before, so you don't know for sure. So we have, I don't know where I wrote E, I meant to write S, subjective. So it's going to be subjective. Probability that the voter chosen at random will be younger than 35 years old is 30%. Classical, empirical, or subjective? Why? It's not an equal chance. And it's probably based off of a survey or some type of study tracking voting habits. Not every single person has an equal chance of going to vote. Okay? Some people just don't want to. Some people aren't registered. So it's going to be empirical. Probability of winning a 1,000 ticket raffle with one ticket is 1 in 1,000. Classical. Everyone has the same chance. Everyone with a ticket has a 1 in 1,000. So we have classical. I mentioned this briefly before, but I just want to talk about it. The law of large numbers. Okay? When you flip a coin, you have a 50% chance of getting heads. Okay? But just because you flip a coin 6 times doesn't mean that 3 of those times will be heads. You may have 4, you may have 5. Maybe you get 6 heads in a row. It's not always going to be exactly 50-50 because it is still random. But the law of large numbers says that the more we do a trial, the closer the empirical probability gets to the theoretical probability. And so while it may vary a lot around our 50% chance, as we start to do it 100, 200, 300, 400 times, it's going to get closer and closer and closer to that theoretical probability. It may never actually reach that theoretical probability, and it may get there, and then the next time we do a flip, it's changed again. Our range of probability is always between 0 and 1. If you get a probability that's above 1 or negative, then you messed up, because it's either 0% or 100%. So if it's 0%, it's not going to happen. It's impossible. The probability of rolling a 7 on a 6-sided die, it is impossible. The probability of rolling a number less than 7 on a 6-sided die is certain. It is guaranteed to happen. And then we have this range of values in the middle. Anything that's approximately 50% is an even chance, and we can even round that a little bit to kind of identify something as an even chance. Around 25% is unlikely, 75% is likely. Now we have this thing about unusual results. And if you're taking psych or you're taking stats before, we know that 5% is kind of that important number. Anything equal to or less than 5%. If the probability of that happening is 5% or less and it happens, that's considered to be unusual. Okay? Because it's such a low chance that it happened. Now, complementary events are all the outcomes in a sample that are not included in the event. When I flip a coin and I get heads, that's my event. What are the other outcomes that could happen when I flip a coin? Get tails. That's the complement. That's everything else. I roll a die, and my event is rolling a 3. Probability of rolling a 3. Okay? I only have one way for that event to happen. I roll a 3. What are all the other options? Other than a 3. What are the other options? 1, 2, 4, 5, and 6. Those are the complement. We denote those with E prime. Okay, that's that little symbol, E prime. And so the thing is, the probability of an event and the probability of its complement always have to add up to 1. And so when we know the probability of an event or we know the probability of its complement, we can use that relationship to solve for the other. And so you'll often see those diagrams with the sample space where inside the circle we have our event, outside the circle is everything else in that sample space. So going back to our previous example, we found the probability of choosing someone 25 to 34 was about 26% for social media. Using the complement, we can figure out the probability of selecting someone that is not 25 to 34. We could just go ahead and add up all of these categories and find a new proportion, but we don't need to, because I know the probability of one event happening. I can also find the probability of the event not happening. So the probability of not getting 25 to 34 is going to be equal to 1 minus the probability of getting 25 to 34. And that's how we get that complement of E prime. And so when we take 1 and we subtract 26, we get our 74%. So we can use complements to kind of fill in those gaps rather than go through and reevaluate a whole new series of events. Probability of non-simple events. Okay, we've got multiple things going on. We'll go into more detail in later units about how to evaluate these a little bit faster, but it's really important to kind of understand the visual. So we're going to use some tree diagrams for these to calculate the probability so that we can look at what the sample space is and what the outcome is likely to be. So probability experiment consists of tossing a coin and spinning a spinner. So we have two things that could happen. We can toss a coin and we can spin it. Okay? Well, the spinner has equal chance to land on one of its 8 numbers, so 1 through 8. So we know that we have theoretical probability. Everything's got an equal chance. And we can use a tree diagram to find the probability of each event. So I'm going to start with the different outcomes on the spin. That's just going to make our tree chart a little bit easier to do. Okay? My outcomes are 1, 2, 3, 4, 5, 6, 7, and 8. After we spin the spinner and we land on a number, we have 2 other possible outcomes, either heads or tails. Heads or tails. Heads or tails. And we can do that all the way down. And so our sample space consists of 1 in heads, 1 in heads, 1 in tails, 2 in heads, 2 in tails, and so on, all the way down the line. Okay? So we have 16 different possible outcomes based on that T-chart, or that tree diagram. If we use our fundamental counting principle and multiply the 2 outcomes from the coin by the 8 outcomes of the spinner, we get the same thing. We get 16 different possible outcomes in our sample space. Okay? So we have a sample space is 16. We want to find the probability of tossing a tails and spinning an odd number. So we need to think about how many different ways that could happen. Okay? So probability of tails and odd. Okay? When we look at tails and odd, okay, if I do this first tree, I get a 1 and a tails. Is that tails and odd? Yeah, okay. If I get tails and a 2, is that tails and odd? No. What about tails and a 3? Is that tails and odd? Yeah. 5, tails and odd. 7, tails and odd. So how many different ways can I get tails and odd? 4. So the probability is 4 possible outcomes for the event out of the 16 in the sample space. So our probability of getting that event is 1 in 4. Then we want to look at tossing a head, getting heads, or spinning a number greater than 3. Okay? And this is very important. It says tossing a heads or a number greater than 3. All right? So it has to be one or the other. So we will look at, okay, well, how many different ways can I get a heads? 8 different ways. Okay? So I've got 8 different ways where I can get a heads. 1 in a heads, a 2 in a heads, 3 in a heads, 4, 5, 6, 7, 8 different ways. How many ways can I get a number greater than 3? Ooh, more than that. because both of those are greater than 3. Those. Okay? So we need to look at combined. We don't want to double up because I'm already counting all of these heads right here. So the total number of ways that I can get a heads or a number greater than 3 is going to be all the ones where the number is greater than 3, all 10 of those, plus that heads and that heads there. So we have 12 different possibilities out of the 16. And then we can simplify our fraction, and that gives us 3/4. So all the different ways that we can get our event divided by the number of outcomes. Last but not least, probability using our fundamental counting principle. Okay, your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can repeat. What's the probability of getting your college identification number when randomly generated 8 digits? So, how many people have any given college ID number? You go to college next year, you get an ID number. How many people are going to have that number? One person, right? One person will have that ID number. So, we have one combination. But, how big is our sample space? Well, it's not 8, because I have 8 digits. And how many options for each of those digits? 10 for each digit. So I have 10 times 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 10. So we get 10 to the 8th power as the size of our sample space. So we get 1 over 100 million as our probability.